let's solve this question. Prove that square root of n is an irrational number. Also prove that a plus b root n is irrational for all a comma b belonging to rational numbers. So let's start by assuming. Let us assume square root of n as a rational number. What is a rational number? A number in the form of p by q, where p and q are integers such that q not equal to 0. So I am assuming square root of n is equal to p by q. The condition here is p and q are co-primes. What are co-primes? Let's consider 6 by 8. Is this a co-prime? No, not co-primes. Because we have a common factor between 6 and 8. We can cancel it with 2. But 3 by 4, the values 3 and 4 are co-primes because you don't have a common factor between 3 and 4. So let's consider root n is equal to p by q, where p and q do not have any common factor, which means they are co-primes. Now let's simplify this equation. Square root of n into q is equal to p. Squaring on both sides, we get nq square is equal to p square. Now when they are co-primes, when you say p square is expressed as n into q square, we can see that p square has a factor n, which means p square is divisible by n. And this is true. When p square is divisible by n, p is also divisible by n. And this statement is true if n is a prime number. So we have p having a factor as n. Now let's consider p is equal to n into some value k. Substituting p is equal to n into k, in this equation 1, we get nq square is equal to n square k square. Cancelling n, we get q square is equal to n into k square. If you look at this, we again have q square as the product of n and k square, which means q square is divisible by n. And same for the same reason, since n is a prime number, we have q is also divisible by n. So what did we find? P divisible by n. We also got q divisible by n. So when p and q both are divisible by n, we get a common factor to p and q, which contradicts our assumption that p and q are co-primes. So it contradicts our assumption that square root of n is a rational number. Hence, we write square root of n is an irrational number as it contradicts the condition p comma q as co-primes. Square root of n is an irrational number, of course, when n is not a perfect square, as it contradicts the condition p and q are co-primes. Now let's prove the second part of the question, that is a plus b root n is irrational for all rational values a and b. Let's assume a plus b root n again as some rational value. Let's consider p by q again. Now let's simplify this. We get b root n is equal to p by q minus a. We get b root n is equal to p minus aq by q, which gives us root n is equal to p minus aq by b into q. If we look at the RHS, we have p minus aq by b into q, where p, a, b and q are all rational values. So the arithmetic operation on rational values will again give you a rational value. So the entire RHS is rational, while the LHS square root of n is irrational, which we have just proved. Hence, a rational value cannot be equal to an irrational value. Hence, our assumption that is a plus b root n is a rational value is false. Hence, we say a plus b root n, or we conclude a plus b root n as an irrational number. Let's solve this question today. Prove that product of three consecutive positive integers is always divisible by 6. Now let's use Euclid's division lemma, which says any number which is divided by 6 either leaves out remainder as 0, 1, 2, 3, 4 or 5. So this is expressed, number when it is divided by 6 which leaves out remainder 0 is expressed as 6 cube, which leaves out remainder 1 is expressed as 6 cube plus 1, then 6 cube plus 2, 6 cube plus 3, 6 cube plus 4 and 6 cube plus 5. So the possible remainders are either 0, 1, 2, 3, 4 or 5. So any number which divided by 6 leaves out remainder either 0, 1, 2, 3, 4 or 5. So any number can be expressed in these forms. Now let's look at the statement. Product of three consecutive integers. Let's start from 6q as a number. Let's consider 6q as one number. The next consecutive integer to it is 6q plus 1 and the next consecutive integer to it is 6q plus 2. So product of these three obviously is divisible by 6 because 6 can be written common and q into 6q plus 1 into 6q plus 2 is an integer part which is divisible by 6. Now let's consider the numbers starting from 6q plus 1 multiplied to 6q plus 2 into 6q plus 3. If you look at the second number, we can take out 2 common from here and we can consider 3 common from the third value. So we get 6q plus 1 into 2 into 6q, 3q plus 1 into 3 taken common, we have 2q plus 1. So 2 into 3, 6 written outside can be written as 6 into 6q plus 1, 3q plus 1 into 2q plus 1. Or let us say the numbers are starting from 6q plus 2. So we have 6q plus 2 multiplied to 6q plus 3, the consecutive integer, multiplied to 6q plus 4. And similarly now we can consider 2 common from here and we can consider 3 common from this. We get 2 into 3q plus 1 and 3 into 2q plus 1 multiplied to 6q plus 4. We don't have to take 2 common here because we already got 6 common. So 6 into 3q plus 1 into 2q plus 1 into 6q plus 4, which also says that it is divisible by 6. Now let's start the value from 6q plus 3. So 6q plus 3 multiplied to the consecutive integer, that is 6q plus 4 and 6q plus 5. The same is the case. We take 3 common from here and 2 common from here. We get 6 times of 2q plus 1 into 3q plus 2 into 6q plus 5, which also says that this value is divisible by 6. Now let's start from 6q plus 4 multiplied to 6q plus 5 into 6q plus 6. In this, it's more easy. You can take 6 common from the last value. We get 6 into 6q plus 4 into 6q plus 5 into q plus 1. Let's consider the numbers starting from 6q plus 5 multiplied to 6q plus 6 into 6q plus 7. 6 taken common from here. We have 6 into 6q plus 5 into q plus 1 into 6q plus 7. It says this product of these values is also divisible by 6. So the number either starts, let's say, from 6q, numbers of the form 6q or numbers of the form 6q plus 1 or anything of this. So from there we consider the next 2 consecutive integers, we multiply them, and in each case we see that 6 comes as a common factor to all this. Hence, the product of 3 consecutive positive integers is always divisible by 6.